My talk, so I used a purposely ambiguous title, current progress and future plans. I'd hope to have more progress, but a lot of it's future plans. So the classic basically the data frame situation is sort of the two sort of key problems, or the two sort of key concepts that we deal with. You can think of it as this, that sort of aren't a natural fit with the Julia language, in some sense, are the idea that we have these heterogeneous columns of data, and some of it's possibly null or missing. And so it doesn't fit natively within a Julia array, so you need some, or any sort of like a classic array in any sort of programming language. So you have these various objects. And so obviously databases are the classic example, but then languages often implement their own various forms of these. So you have data frames in R, plus their variations that try to improve on that. You have pandas, and then you have all these various new in Python, you have these various new frameworks like Spark and S-frames, which are trying to do sort of even great modern crazy things and distributed versions of all these same idea. But they still all boil down to these sort of two key problems of heterogeneous columns and null or missing data. And in Julia, there's been a couple of approaches to this. The oldest by far is data frames. And then obviously I'll plug the other two, type tables, really next. And the JuliaDB and the data stream stuff, which Jacob's talking about tomorrow. And there's been a few other things as well on the way. So data frames itself is very old. In fact, it's package number 6, registered in metadata. And that includes example, so really 5 of the useful packages. It's somewhat, it was very, very much inspired by R. Basically, it was built to fill the niche of the R data frame, and so it built a lot of semantics from that. But it's also grown somewhat monolithic and has basically inherited a lot of cruft from trying to accommodate multiple Julia versions and the changes that have happened since 0.1, 0.2, 0.3, 0.4, and now 0.5. As you get all these changes, you have to then keep switching semantics and these sort of things. The format's fairly simple, and it actually works. It works remarkably well for something. It works quite well for the problems it solves. It does nice things like display HTML automatically in Jupyter Notebooks. Okay, so the classic iris dataset. I'm a statistician by training, so obligated to use the iris dataset. And that's sort of the classic. It's got a nice example. It doesn't actually have any missing data in this, so it's probably not a good example in that sense, but it does have heterogeneous columns. So it's got some data, some numeric, some text. So I guess I'm continuing a theme on here. So John Miles White gave a talk last year about data, extensively focused on data frames and how to improve it. So I wasn't at the talk, and he's not here this year, so I get to recover the whole same material again. But the core problems boil down to it's sort of not amenable. The way it's structured is not amenable to the optimizations that Julia can do, which namely sort of type inference and the various things that are built on that. And to get around those sort of these performance bottlenecks that result, it leans very heavily on sort of the vectorized operations. Again, this is partly due to its R heritage, which is what it was, which again, they're the tricks it uses. And the problem is it's not very extensible because of the interface and how you use it is very tightly coupled with what it is actually underneath. And so to give you an example of what happens here, so the classic type inference problems, if you want to pull a column out, because you're indexing by a symbol, Julia's unable to figure out what the exact type is of the column because it can't infer that at compile time. So this is not so much a problem when you're pulling a whole column out, but when you're trying to do loops, it becomes a bigger problem. And then the second problem is each column is itself what's called a data array, which is basically a way of, again, to represent missingness. You can either be a type or a or this NA type. And so when you index an element of that vector, it spits out, it's unable to infer what the type is, and it thinks it's a, well, this is the money. This is the bit we care about, is the, it thinks it's either an NA type or a float64, but is unable to figure that out. And so as soon as you get union types in Julia, this is sort of a performance, black hole, because it has to suddenly start doing boxing and all, runtime dispatch and all those ugly things. That causes bottlenecks. So if you're Arch's talk yesterday, he sort of gave the big overview of what of why this is a problem. And so to get around this, as I said, very much encourages vectorized operations, which is what R and Python and stuff have been, R and pandas have used classically, because rather than operate on individual atoms, you try and operate on vectors and then write fast kernel operations that then work on these vectors. And so here, for example, I'll use a running example of like a filter operation. You want to filter rows. You use the dot syntax to dot greater than dot inequality to get an inequality across to get the vectorized form of the inequality, and then you then subset on that. Which isn't such a big problem when you're only doing one, but if you're doing multiple, then you end up with somewhat awkward syntax and a lot of allocation. So if I want to subset on two variables, it firstly has to create 3 intermediate arrays. It has to create one for the one comparison, one for the other comparison, one for the joint, and then so that's 3 intermediate allocations of Boolean arrays, and then do the subsetting from there. It also gets somewhat awkward. You have to use these kind of crazy, have to use a lot of parentheses. You have to keep writing the name Iris everywhere, which gets a bit awkward after a while. And fundamentally, it just doesn't match the rest of the Julia idioms. We do all these other, Julia has very much been focused from the get-go on having fast loops, just being able to write a loop as opposed to having to use vectorized operations, and this is sort of just going back against that. So it seems like we shouldn't, this is, if we're doing this, we're doing something wrong in some sense. And we can't use the double ampersand operator there, for example, because obviously, well, it's basically because we have a vector, not a single element. And sometimes just things randomly break because they're missing methods. So for example, all I did was switch the order of the arguments in the and it turns out that for some reason this is missing a method. I think the problem is here, this is actually giving you a different type of array, apparently. The fact that this arises is a sign of the sheer complexity. And if you look at the code, it is really defining a bunch of methods that shouldn't need to be there. And then I guess the bigger problem is then, okay, it's all good and well if you have the vectorized operations, but what if you don't? So you want to use some other predicate which doesn't have a vectorized form. Then you have to start using maps, and again, then these predicates don't have a special unionized. If they don't have the special union handling, then they'll be consequently slower, and so everything just gets much more complicated than it need be. And then the other problem is the whole data frames experience is very much tightly coupled with this underlying representation. So we're operating, it treats all the operations as operating on vectors, but you don't really want to be operating on vectors if you don't have to. I mean, if you've got all your data in a database, it makes sense to leave the sort of computation until try and do all this in the database, and then pull it into your program. So that sort of thing. And this becomes also a bigger problem, for example, if you want to use some sort of disk-based array, you don't want to keep doing, if you're playing compound operations, you don't want to read all in from the disk into memory, into the processor, do all the computation, then write it all back out again, only have to read it all in again. You want to do all these compound operations in a much more efficient way. So in some sense, just trying to pretend things act like, trying to treat data frame columns as vectors is, I think, ultimately a dead end. So fundamentally, what can we do? I think the first thing is, you don't want to require the columns to be data arrays. So the idea of these heterogeneous columns and the missingness having two different, they're really orthogonal concepts. They're, you don't need just because you don't have to have columns of missing data, with missing data. So you should be able to stick an ordinary array in there. I think would be a good design choice, and that's something hoping to get done in the future. But it also then allows you to use more efficient storage mechanisms. So you can use like sparse arrays or run length encodings and that sort of thing to get more compact representations. So the next thing is alternative handling of missingness. And this is something that's been a bit of discussion about, but hasn't really had a concrete solution yet. And so the one that's probably received the most focus, if anyone's been following this, is the idea of nullable wrapper types. And this, the idea basically is rather than returning a union, like either returning the value or an NA, you return this object, a nullable, which contains, which may or may not contain the object. So to give you an example, we create this is using the nullable arrays package. So it looks like so if we index into the first element, you get a null. If you index in the second element, you get a 2 wrapped in a nullable object. And the nice thing about this is that this is completely type stable, gives you a concrete return type. But the problem is you're then stuck with this object that's wrapped in a nullable wrapper. So you can't use it directly. We can't just add 2 to it because you can't add 2 to it. It's a nullable object. And so what do you do with here is you end up with sort of this decision. Do you then go defining, you need a way to sort of lift the nullable object out of need to lift the value out of the function out of the nullable object. Not sure how that lifting works anyway, but the analogy works there. But basically, we need a way to say if it's a nullable, do the operation, otherwise return a nullable. So one way to do this is using dispatch. So for example, we define a function add 2, and then if it's nullable, we check if it's null, return the null object back again. Otherwise, we add 2 to it. And so this works as required, but it's again somewhat brittle because it requires you to go add this lifted form to every single function you ever want to use, which gets you so far, but it gets kind of complicated after a while, and it makes it hard to do things like use anonymous functions, use all these other things that we want to be able to do easily. The other approach, which is slightly better, I think, is to incorporate the lifting into higher order functions and then use those, encourage use of that. So that seems like so for example here, what you're doing is you define a map function, which you find the map function to do the lifting itself. And so that will check if it's null, do the addition, if not, otherwise return a null back. But there is an alternative approach, and I think this is worth considering. But fundamentally, the nullable idea sort of originates in static languages. Particularly, obviously the canonical example is the maybe in Haskell, I guess. But Julia fundamentally is a dynamic language, and so the fact that we have union types means we should be able to use them. So, and so the fact that they're slow isn't a consequence of the language; it's more a consequence of the implementation. So we could fix that implementation. Unfortunately, that would require quite a reasonable amount of architectural change. So it's probably not going to happen anytime soon. But it would. I think ideally would be the perhaps the nicest solution to this problem. So the another approach is to stick more, so getting away from the missingness problem is talking about this column type information. So how do you index into columns? I won't talk too much about this because obviously this is the type tables is coming next, but I will point out that sort of similar ideas do pop up, and the notable one being this idea of structs of arrays. And this is how you sort of can efficiently store a vector of structs, is that you instead of a vector, you instead store it as a struct of arrays, basically. So, and there's a very nice package called here, which does basically is doing very similar, is doing very similar ideas under the hood. Unfortunately, this does cause some challenges, which is, everything has a trade-off. If you stick the type information in the type itself, then you can no longer change the type of an object. We can't use symbols to index because you don't get the typing for its benefits, so you have to do awkward things like use vowels or macro tricks. And it does cause significant JIT overhead. And this is something which you have to be somewhat careful about because if you need to start doing more runtime dispatch, then you might spend more time generating code than you are actually doing the computation. And so you're back to where you start. In some sense, just putting a problem somewhere else. And so I'm not sure if this is, I think it's worth exploring, but as to whether I'm not 100% sure it's the solution we want to push for. And so finally, the thing I want to end on is the idea of focus on a more descriptive way of describing transformations. And so this is the idea, this has been around for a while. The idea is basically we have a separate language or sub-language that describes the transformations which then get transformed into the operations that you want to perform. And then the idea is that this can be, support multiple backends. So if you have a data frame or a database or whatever, or you want to use Spark in the backend, you can do all that in Julia and it'll just transform it into the code you need. And so, the canonical example is not really an embedded language, but is sort of the standard for descriptive query languages, obviously SQL. And so you have things like so this is my filter statement I had earlier, which is nice. That's fairly simple, but as SQL queries get bigger, you have to start worrying about semantics. It's also not, I always find it can never quite remember the order of evaluation if you start doing more complicated things. And so it's useful, but isn't, I think, the last word on the problem. So probably one of the better more innovative solutions here in this area has been the dplyr package in R. For those of you who haven't seen it before, basically the idea is that so my subsetting clause here, filter clause here would work like this. It looks a bit awkward because what it's doing, it uses heavily what R calls non-standard evaluation. Basically means it evaluates this expression in the context of the data frame itself, not in the scope it's doing. So this is quite useful because it means you can do, you don't need to quote column names or do anything or do other awkward things. But it does give you very weird scoping behavior. So for example, you have a variable called species. Which one is it in a scope? Which one are you using? You get even bigger problems if you, the canonical example as well is if you misspell them, then it causes really big problems because you're never quite sure which you're looking at. Especially, I think R has some crazy feature where it actually looks up, it tries to guess close misspellings. And so it's a great way to shoot yourself in the foot. But one other feature it does have is this idea of this pipe operator, which basically allows you to sequentially build up more complex operations. So you first filter, then you summarize, etc. It has ones like grouping and these various operations. And then the feature that makes it really powerful is that when you use this with a database as opposed to a data frame, it can construct, all it does is essentially build up that SQL query I mentioned earlier, and then when you actually want to pull the data out, then sends it out and evaluates it. The other great example, and that has required serious thought, is the link in the C# and various .NET languages. They provide like a SQL-ish syntax embedded in the language itself, though they rearrange the order of operations to actually make sense. So you put the data frame, the object you're pulling it from first, and then as opposed to the SQL, which kind of inverts everything. And it also provides a short form of the function, a short form which takes that takes sort of lambdas to get you that you can use quite easily. So how could you go about doing this in Julia? That's something I've been thinking about recently and playing around with. So the first thing is that you want to avoid unnecessary use of strings. So people have tried this in Python, but end up basically what you end up with like the stringly typed problem where you just shove everything in a string and then write some parser that then reparses that string and evaluates it. You want it to be conceptually consistent, and this is particularly important in Julia because it makes Julia has always made distinguishes between vectorized and scalar operations. So if you notice back in the R example, I just used the standard greater than rather than the dot greater than. So the question is petal length here a value? Is it, when you start worrying about vectorized operations, you have to think carefully, is this actually a column or is it an element in a column? And those semantics matter, and I think it's important to be consistent there. The other thing is the scoping rules. Obviously, you don't want to end up with a mess of where it's ambiguous about which variable you're referring to. You want it to be clear and understandable, and both easy to read, but it's easy to both understand what it does and, more importantly, how it does it. So it gives you a clear conceptual model of what you're trying to achieve, like what is going on under the hood, which again is one of Julia's strengths and something you want to maintain. And something that I've come to appreciate is you want to minimize the number of unnecessary keystrokes. So you want to limit parentheses, quotes, strings, arrows, etc. Just if you end up with these really complicated expressions, it just makes it more hard to understand. And then you want it to be ability to build fast code. So there has been actually some effort on this. I should mention, so data frames meta has been around a while as well, and so this was mostly written by Tom Short, who has also responsible for large slice of the data frames itself. And it uses a few metaprogramming tricks. So for example, this filter operation I mentioned earlier, at where, so you would write using data frame at where, and then so you just use symbols to refer to columns. And so symbols are then replaced by the columns itself. So it's quite nice. It works quite nicely. But the symbols are referring columns, so it solves a scoping issue, but it gives you this sort of weird syntax issue where, okay, what if you actually need to refer to a symbol? And it's also a bit of a syntax abuse, I guess. It does again still use vectorized operations, so which again to work around those type instability issues I mentioned earlier. And then it is also finally very tightly coupled with data frames, so you can't get out of that. So it doesn't solve that sort of back-end issue. So perhaps a way to think about it is, okay, what is the fastest way to filter? So what do we want to write? What the code we want to generate, I guess, in some sense. And so in Julia, I think this ends up being sort of the fastest way I can figure out how to do this, which is actually in 0.5. Now we have fast anonymous functions. So you want a subset on a bitmask vector. The bitmask vector is generated by basically you want to pull the columns out first because that's and then pass that to a function which is then able to use the fact that as soon as you pull the columns out, it's then inferred the type. It then knows the type, so then it can pass that to the fast loop function. And so this seems to be the cleanest way I've come up with doing this. And so how can we go about getting that? The next question is, how can we minimize keystrokes? Well, so the simplest way to write that sort of where expression that I could think of is exactly that, so what I had earlier. So how can we get from this to what I had previously? And more importantly, how can we do that without using eval, because eval is evil. So this is what I came up with, is this little neat macro. Remarkably few lines of code, although it does have another function. 5 minutes, perfect. Basically, so pass it in, and so I used Mike's nice macro expand trick. Basically, what it does, it just transforms that expression. So at filter will transform that expression into the desired what we had earlier. Uses slightly different variable names. That's just the result. The hawk and squirrel are just the way of getting rid of the gensim ##3 things that you get during metadata. At filter, and so yeah, it does exactly what you want it to. And also this makes it very easy then to include non-vectorized functions. And the nice thing about it is that it turns out you can actually use $ to prefix variables in macros. So it's not valid Julia syntax, so you don't have to worry about it conflicting. And it makes it clear which variables are in scope. So if I want to refer to a variable outside of the scope, I can just stick a dollar sign in front of it, and it then it replaces that with the actual variable itself as opposed to the thing. And again, doesn't require using eval. So that's sort of the things I've been playing around with. It does lead to a bunch of open problems that I'm still trying to think about. How to get a nice chaining syntax. So this is just one function, but you usually want to do a bunch of operations. So could we we've got Julia has this pipe operator, so can we build on that? Then how you can construct sort of the lazy SQL statements from that at filter. Should be fairly straightforward because the macro has access to the syntax tree in the nice form it already needs. So that's what I'm trying to work on now. And finally, and this is the sort of I have to think this through a bit more, but we need to establish clear scoping rules. So for example, what does this do? I'm not quite sure yet, and so maybe we shouldn't allow that. Okay, and then there's a final thing is there's a lot of actual complicated transforms that aren't that need to think about. So the common one is like stack and unstack. If you want to go from the tall format to the wide format, and that sort of thing. So these are some open problems, and if anyone has like great ideas, I'd be keen to hear them. Thank you. Oh, yes. Yep.
Yeah, okay. So you talked about I think several slides back, the most efficient way to do the filter operation, and it involved creating a bit vector.
Yep.
And I was just curious, that seems like a bit of overhead that might not technically be necessary because you're still creating that array and then filtering the data frame based on the output of that array, or what the contents of that array, rather.
Would I put that?
Any thoughts on that?
Yes. So I think that is one case. Yeah, there's the obvious trade-off because so if you assume your back, so this is the fast version was assuming the backend format was actually the classic data frame, so a bunch of vectors. And so if you're subsetting multiple vectors, it does seem to be quicker to just generate a bit array rather than go through it and sequentially. You're right, there is a trade-off there. And I did a little bit of profiling in this, obviously not on a iris, which is 150 data points, but yeah, it's something you'd need to explore, and there probably is some trade-off there. But this does only require one bit array, as opposed to 3 or 4 or more that you would usually construct. So, and it seems to work quite well. So, but yes, there's the nature of these things. There's always trade-offs.
That makes sense. Thanks.
Yes.
Hi, I think this is obviously a very hard problem, and it looks like great stuff. So I'm really glad that there's people working on this. With this design, I mean, this is a problem with lots of things. Like with Spark, they have the data frames. They have their Spark SQL engine that does some optimization of what the calls are, and it's not in the data frames, so not accessible, which is a similar problem because they want to use type inference. They do things in Scala, but they have this data sets thing that's kind of new. Have you looked at that at all? And because the language with Scala, with the lazy evaluation, is also very similar, at least from an outside perspective, to what we're trying to solve here and what Julia capabilities are. So.
Yeah, exactly. I haven't looked extensively. I mean, I'm aware of aware of the Spark and how it works and like the idea of it. I've never actually used it in Anger, so haven't sort of used it extensively. But it's a similar problem, and I think it's kind of interesting that despite coming at it from a completely different point of view, they're trying to solve the same problem as sort of dplyr was as well. It's like you don't want to have to reevaluate everything on each operation, but you want to have a nice clear semantics for expressing a sequence of operations that can then be applied lazily. Yes.
I like the way that DeepWire has solved this problem, but it solved it in part by creating yet another in R.
That's certainly true.
On top of a whole pile of other data types that we have to solve exactly the same problem. And we're talking about doing exactly the same thing in Julia here. And I'm worried about that. But yesterday, when we were seeing how array firing things work, they at least some of them inherit directly from abstract array, so that we can handle them like they're all arrays, even though they may be implemented in completely different ways on GPUs, in file systems, and whatever. And I'm just wondering whether there's some abstract data frame that we can create that has commonalities between all of these different, I mean, I don't know what the type of arrays are, but all of these different types, so that we don't have to choose one of them and never speak to anyone else again because we don't understand the syntax for this other type. I mean,
Yes, certainly.
There's enough in common that we can create an abstract.
Certainly. And I think that's important, but actually nailing down the trait, nailing down what it should be is remarkably difficult. I mean, it's difficult enough to define what an abstract array is itself. Like, is a range an abstract array? What are the things that make an array an array? And it gets even more complicated with data frames because you have this suddenly, now heterogeneity. You have the missingness, obviously, and then you have other things like how you query it. Is it row oriented? Is it column oriented? These sort of things.
But that may be a speed issue, but it's not necessarily an issue to do with
No, it's true.
to do with how you address them. I mean, if we're talking about something that's backed by some PostgreSQL database, then it's going to be there are going to be different implications for how we handle it quickly. But nonetheless, if we can just say this is going to be some kind of a table, some kind of an abstract table, and then everything handles it the same way, then all of this becomes a lot simpler. It seems to me. I mean, I don't dispute how hard it's going to be to come up with the abstract thing, but it just seems like something that's worth doing sooner rather than later.
I agree. Unfortunately, I mean, I agree. Unfortunately, I think you only come across that when you've tried it. You've tried implementing it 3 or 4 times, and you finally hit upon what those sort of key ingredients are. I mean, that's the nature of these things, that you have to try it and see what works and what doesn't work, and then you iterate and fix it again.
I would point out that one big difference between Julia and R, for example, is that R already has this ecosystem-wide commitment to the data frame type. And so even if you come up with something better, there's just no way to rip out the data frame at that point. It's too late. So we don't have that, which is both like a blessing and a curse. It's kind of nice that everything works with data frames in R, but in Julia we can actually come up with something that is, we'll work on array fire and we'll work on, multi-core CPUs and out of core, but we have to do that. So, Simon, thank you.
Thank you.